And in this section here, 4.5, we're going to talk about a function's limits at infinity. We're going to determine finite limits at infinity, determine the horizontal asymptotes of the graph if it does have any, and determine infinite limits at infinity. Now, way back in Chapter 2, we did talk about limits before, but we were more interested in the limit as we approached a point on a graph or a hole in the function. Remember, we had something like this. Maybe there was a hole in the graph above +2, and we were looking at the limit as we approached that hole in the graph from above and below. Or maybe in a function like this, we would look at the denominator and say at +2, we're going to have a divide by 0 scenario, so we're going to have an asymptote there. And then we were interested what this function did as we approached from the left or the right. As we approach from the positive side, we'd take off to positive infinity, and from the negative side we'd head off to negative infinity. We had that x, or value of 2, was a horizontal asymptote. In this section, we're more interested in what's going on at positive and negative infinity, or the end behavior of these functions. In the last two sections, we were looking at functions and determining the interesting points, such as mins and maxes, points of concavity, or points of inflection where our concavity switched from up to down. And another thing to look at on a function is this end behavior. What does the function do at the extremes, at positive and negative infinity? So here, this section discusses this end behavior of a function on an infinite interval. Consider the graph of this function. We got 3x squared over x squared plus 1. If we look at the graph here, we see we cross through the origin, and as we start heading out the x-axis toward positive infinity, it looks like our function, it's increasing, and then it's leveling off. And it looks like we'd have this x or y value of 3 as a horizontal asymptote. And the same thing as we send x off to negative infinity to the left, we see the same behavior. The function's increasing, and then as we get farther and farther out, we're getting closer and closer to that y value of 3. But it doesn't look like we're ever going to get there or touch it. So it looks like graphically we approach 3 as x increases or decreases without bound, and we could put this function into our calculator and bring up that table feature, and we could see the same thing numerically. Here at 0 we're at the origin, and then as we head out, we start plugging in bigger and bigger numbers into our calculator. We see that our y value is increasing, but it's getting less and less the closer we get to a y value of 3. Same thing as we head off to negative infinity. And the table suggests that the value of the output, the f of x, approaches 3 as x increases without bound, or as x approaches infinity. And similarly, as we decrease without bound, head x off toward negative infinity, it seems like we're approaching that same asymptote at 3. And how we would denote this limit at infinity, we would say the limit as x approaches infinity of our function f of x is equal to 3. And from the other side, we could say the limit of our function f of x as x approaches the negative infinity, that would also be equal to 3. Now a little note down here. Yeah, the statement, the limit of f of x as x heads to negative infinity equals L, or the limit as x goes to infinity of f of x equals L, means that the limit exists and it's also equal to L. Remember, L is just a real number on our y-axis. Now here's our formal definition of a limit at infinity. Remember, we had our definition of a limit before, and we talked about these epsilon neighborhoods. These plus or minuses are sort of like a margin of error around the number that we're focusing on. So the definition might be a little confusing. Hopefully we'll clear it up a little bit with the graph. And here it says definition of limits at infinity. Let L be some real number, and graphically that's a line on our y-axis. That's a real number. Let L be a real number. The statement, the limit as f of x approaches infinity is equal to this number L, means that for each epsilon greater than 0, there exists an m greater than 0. such that the absolute value of the f of x minus L will be less than epsilon whenever x is greater than m. Now that's quite a mouthful. Well, let's try to break it down a little bit. And this just says the limit as we head off to infinity is equal to L. That's this height here on the y-axis. It says for each epsilon greater than 0, or each positive epsilon. Again, that's just a little plus or minus, a margin of error around the limit we're looking at. So this just says you can pick any little tiny epsilon neighborhood, make it as small as you want, and no matter what, I can find an m value greater than 0, and that's just a number on our x-axis, such that I can pick an m value, and the difference between the limit and the actual y output is going to be somewhere in that epsilon neighborhood whenever you pick an x bigger than that m value that I gave you. So again, real quick, you can pick a epsilon, just give me a little tiny, say I want to be that close to the limit. I want to be really, really close. And if you give me that epsilon neighborhood, I can say, well, no matter what, I can always give you an m value here on the x-axis and say if you want to be inside that epsilon neighborhood, all you got to do is use an x value bigger than this m value that I just gave you. You know, that's all this formal definition is saying. It says no matter what, I can always pick that m value to get you in that epsilon neighborhood that you want. And that, you know, we have a similar statement number 2 here for negative infinity. It's the same. I can find an x value less than n. I would just, you know, reflect this over here on the other side, and over here we'd call it an n value. And if you wanted to give me a little tiny epsilon neighborhood, a little margin of error, and tell me you want to be that close or closer, I'll say, well, if you want to be that close, you at least got to use an n or an x value that's less than this n value that I just gave you. So the definition of a limit at infinity as shown in the figure. In this figure, note that for any given positive number epsilon, there exists a positive m, such that for all x is greater than that m, the graph of the function f will lie between the horizontal lines given by y equals the limit plus epsilon and minus epsilon. And that's just that epsilon neighborhood around. And you know, if you don't completely and fully understand this definition, you know it's not the end of the world. It's not going to sink you for the rest of this class. Horizontal asymptotes. In that figure, the graph of f approaches that line, y is equal to L, as x increases without bound. The line y equals L is called the horizontal asymptote of the graph. Remember, we had our vertical asymptotes in chapter 2. This is just the same thing. An asymptote, you know, it's a line we're going to get closer and closer to but never really settle on or touch. So here's our definition of a horizontal asymptote. The line y equals L is a horizontal asymptote of the graph if the limit as we approach negative infinity of the function here f of x is equal to L, or the same thing for positive infinity. The limit of our function as x approaches infinity is going to, you know, get closer and closer to this value of L. And note from this definition it follows that the graph of a function of x can have at most 2 horizontal asymptotes. You know, maybe we'll have one asymptote as we head to positive infinity and a different asymptote as we head off to negative infinity. These limits at infinity have many of the same properties from limits we discussed in an earlier section when we were looking at the limit of a point, or as we approached a point from either side. And 2 of those properties were sums and products. And we have here the limit of a sum. You know, here's our 2 functions, 2 different functions, f of x and g of x. The limit of the sum of these functions is equal to the sum of the limits. We can break it apart and say the limit of the first function f of x plus the limit of the second function g of x. Those are exactly the same. Again, just like the limit properties we talked about in chapter 2. And the same holds true for products. The limit of a product is equal to the product of the limits, if that rings a bell. It's almost like we distribute the concept of a limit. The limit of the first function f of x multiplied by the limit of the second function g of x. And these properties do hold correspondingly as we head to negative infinity. So here's a theorem for this section, theorem 410. If R is a positive rational number and C is any real number, then. And here it just says C is a real number, so we got rational functions here going on. And the first one is the limit as x go to infinity of C over x to the R. And from our definition, C is just some real number like 2 or 3 or 5. And underneath it, in that denominator, is some value raised to a power. R is a positive rational number. And the x value, x is going to infinity. So the scenario here is a finite numerator divided by an infinitely growing denominator. And as we have a finite numerator divided by something larger and larger, as we head off to infinity, our limit, we're going to approach 0. And that's also true as we head to negative infinity. Again, we have a finite numerator, either positive or negative. We're dividing it by an infinitely bigger and bigger denominator. And that's also going to head off toward 0. This second limit here is only valid if x to the r is defined when x is less than 0 or when x is negative. And property number 2 here, now we're dealing with e to the x. So as we take the limit, x approaches negative infinity of e to the x. That limit is 0. If we remember just basically what the graph of e to the x looks like, or any exponential, we always cross at the y value of 1, and we're heading up. So the limit as x heads to negative infinity, we're heading our x values off this way, and it looks like, this is going to get smaller and smaller, closer and closer to the x-axis, but never touch it. So we're heading to 0. And the second one there, the limit as x heads to infinity of e to the negative x is also equal to 0. Now remember, e to the negative x, we could rewrite that as 1 over e to the x. And this limit we're talking about, we're heading off toward positive infinity. So I'm going to have 1 divided by a growing larger and larger denominator, e squared, e to the third, e to the fourth, e to the 100th power. That denominator is going to grow very large. 1 divided by an infinitely large denominator is heading off toward 0. So the limit as x goes to infinity of e to the negative x is going to head also to the x-axis as a horizontal asymptote. And we can use these properties here that from these last couple of slides to look at example 1. So it says evaluate the limits at infinity. Our limit, our x value, is headed off to positive infinity of this quantity, 5 minus 2 over x squared. Well, we have two terms here inside the parenthesis, and remember, we can think about this as two separate limits then. The limit as x goes to infinity of 5 minus the limit as x goes to infinity of 2 over x squared. And then we can look at them separately. This, if we graphed it, would just be a horizontal line at y equals 5. It doesn't matter as x goes off to infinity. If here's our horizontal line at 5, as x heads off to infinity, we're just having a y value of 5. So there is no x value in this to plug a larger and larger number into. This value is just 5 minus. Now we're sending x off to infinity. We have a finite numerator divided by a growing larger and larger, infinitely larger denominator, and by our property up here in theorem 410, that's headed off toward 0. So 5 minus 0 is 0. The limit of this function is 5. And here in example B, it says we want to find the limit as x goes to infinity of 3 divided by e to the x. If we use our properties of exponents, we can rewrite this. We have our limit as x goes to infinity. 3 over e to the x, we could also write as 3e to the negative x. Bring that exponent up, or that whole denominator up, and make that exponent negative. Now it looks like our number 2 up here in theorem 410. We have the scenario where e is headed off toward, or x is headed off to infinity of e to some power, negative power. So we know that that limit is going to be equal to 0. Or when I look at this, from the very beginning we have 3 over e to the x. And we know our x values are getting infinitely large. When I look at this, I almost see a case of property number 1 up here from our theorem. I have a finite denominator, or numerator, 3, that's not going to change. And I know that my denominator, I'm going to plug larger and larger values in for x. E to bigger and bigger exponents is an infinitely large number. So that's going to divide out to equal 0. Either way looking at it, I guess, would be valid. Okay, example 2 here. It says finding limits at infinity. So first, let's see what happens if we just, remember direct substitution back when we were looking at limits was always our first attempt. So here, let's see what happens if we stick infinity in for x. If we look just at the numerator, we're going to have 2 times infinity, which is infinity, and then just minus 1 is nothing, so our numerator is infinity. And if we look at our denominator, infinity plus 1 is infinity. When we get this, remember we had 0 divided by 0 was indeterminate form. Infinity divided by infinity is also indeterminate form. Indeterminate form. So because we have this indeterminate form, we can't make any conclusions about this limit at infinity. We're going to have to play around with it a little bit and try some stuff and see if we can whittle this down. Remember, if we do something to the numerator of a fraction, we also have to do the same thing to the denominator of a fraction. And what we're going to try here is dividing both the numerator and the denominator by x. And I'm going to do each term separately. So here in this numerator was 2x minus 1. I'm going to do the first term divided by x and the second term divided by x. And I got to do the same thing to the denominator. So the first term was x, I'll divide by x. And then I also had a plus 1, and that's also divided by x. Now let's take a look at this as we send our x value off to infinity. Well, first, these are going to cancel. So this is just going to be a value of 2 minus. And then we have a finite numerator divided by an infinitely large growing denominator. That turns into a 0. Finite divided by infinite will be 0. In the denominator, our x values will cancel out. So here we're just going to have a 1. And then plus finite numerator divided by an increasingly large denominator heads to 0. So here our limit is 2 divided by 1, or just plain old 2. I got a little note here. It says, when you encounter an indeterminate form, such as the one in the next, or example 2, you should divide the numerator and the denominator by the highest power of x in the denominator. Highest power of x in the denominator. And if we take a look at the graph of this function here, we knew from the original function we have an x plus 1 denominator, so we'd have a vertical asymptote at a value of x is negative 1. So there's our vertical asymptote. And now as we head off toward positive infinity, we're heading off to positive infinity. Here our x values are growing along the x-axis, and we're going to head off to and get closer and closer, but never quite attain positive 2. And this is summed up here, and your notes are in this box. Guidelines for finding the limits at positive and negative infinity of the rational functions. If the numerator's degree is less than the denominator, the limit will be 0. If the degree of the numerator is equal to that of the denominator, then the limit of the rational function will be the leading coefficients. And if the numerator's degree is greater than denominator, the limit of the rational function does not exist.